Hello. In this session, we will review the largest changes delivered as part of JDK 19, the most recent release of the Java platform. JDK 19 is the second release of 2022 and the 11th release since we switched to a semi-annual release cadence. JDK 19 replaces JDK 18 and will be superseded by JDK 20 in March of 2023. The next LTS release is JDK 21, due out in September of 2023. JDK 19 is released under the no-fee terms and conditions, so everyone can use it in production at no cost. JDK 19 brings us 7 JDK enhancement proposals. It will be a preview rich release, with 6 of those JEPs delivering either incubators or preview features. There are 2 JEPs with language features from Project Amber, 2 with library enhancements from Project Panama, and the first set of preview features from Project Loom, which aims at making it easier to write multi-threaded applications that properly utilize available resources. Lastly, the only non-preview or incubator JEP is a port to Linux RISC V. Let's look into each one of these JEPs. Pattern matching for switch builds up on the work started in JDK 14 with the changes to the switch statement and pattern matching for instance of from JDK 16. This JEP brings those two together and introduces pattern matching into switch statements and expressions. Let's see an example. Switch statements used to work only on a few types, numeric, enum, and string. With switch expressions, we introduced other case labels, but you still couldn't use a switch statement to test expressions against multiple patterns. Until JDK 19, we still would have had to chain a bunch of else-if statements. Using pattern matching in a switch expression, we can make this clearer. And as a bonus, this code is optimizable by the compiler. Remember that the case statement has to be exhaustive, so in most cases, you want to add a default value. Notice that you can also now add a test for null as another case, making the code even easier to read and maintain. To maintain backward compatibility, the default label does not match a null selector. After a successful pattern match, we often need further tests, which can lead to cumbersome code like this. We can improve readability if the pattern supported a combination of pattern and Boolean expressions. So, allowing when clauses in switch blocks allows us to write these in a cleaner way. The first case matches strings of length 1, and all other strings are caught by the second case. The when clause can use any pattern variables declared by the pattern in the case label. In earlier previews of pattern matching, rather than when, we used the short circuit AND operator, that's the double ampersand. But that became confusing if the expression used Boolean operators. So in this preview, this was changed to use the when keyword. There are a couple of new gotchas that arise with pattern matching for switch. The first one is that pattern could dominate later patterns. It is possible to have an expression that matches multiple labels in a switch block. This is allowed, but they must be placed in the right order. Here, we have code very similar to what I just showed you, but with the order of the case statements reversed. Since the first label will catch all strings, including strings of length 1, the second label is never reached. It is dominated by an earlier case. This will result in a compile time error. This is one area that has received some improvements from the first preview in JDK 17. Constant labels now have to appear before a gathered pattern of the same type. Another new possible error is to have fall through when declaring a pattern variable. In this example, if the variable was a character, it would print character, but then, as there is no break statement, execution would flow to the next case label, and since the variable I declared in the second pattern would not have been initialized, we would get an error. It is therefore a compile time error to allow flow through to a case that declares a pattern. Falling through a label that doesn't declare a pattern is fine. The next JEP in our list, Record Patterns Preview, also merges functionality from 2 prior enhancements. It allows the use of records and pattern matching, both of which were introduced in JDK 16. Let's look at this example. The pattern variable p is used here solely to invoke the accessor methods x and y. It would be better if the pattern could not only test whether a value is an instance of point, but also extract the x and y components from the value directly. In this example, point integer x integer y is a record pattern. It lifts the declaration of local variables for extracted components into the pattern itself, and it initializes those variables with the right values from the past object. The true power of pattern matching is that it scales elegantly to match more complicated object graphs. For example, consider the following declarations. Let's make the point more complicated. We introduce a color. Then we define a color point as a point and a color. And finally, a rectangle is defined by two color points. We know we can extract the components of an object with a record pattern. If we want to extract the color from the upper left point, we could write, but the color point for the upper left is also a record, which we can decompose further with nested record patterns. Using nested patterns, we can decompose the outer and inner records at the same time. A record pattern can use var to match against the record component without stating the type of the component. Note that the names of the pattern variables do not have to be the same as the names of the record components. Foreign Function Memory API incubated in JDK 17 and JDK 18. This JET promotes those APIs from Incubator to preview features. This also illustrates the relationship between incubators and previews. These APIs make it much easier and safer to have Java code interoperate with C libraries. The goal of these APIs are to eventually replace the existing Java native interface with something that is better in terms of lower complexity, superior or equivalent performance, and to grant access to foreign functions written in other languages besides C. This last part is not yet there in the preview. These APIs won't lock developers out of unsafe operations, but they will be better at warning them when they're doing something potentially unsafe. Vector computations allow systems to execute operations on vectors instead of applying the same operation to several values one at a time. This can result in significant performance improvements. Hotspot supports auto-vectorization, so sometimes it can detect when scalar operations can be transformed into superword operations and mapped to vector instructions. The set of transformable operations, however, is limited and fragile to changes in the code shape. This API will make it possible to write complex vector algorithms in Java in a way that is far more predictable and robust. Here's a conceptual model of a vector operation. Instead of needing to repeat operations, we can achieve the same result with a single pass. As everyone who reads random Wikipedia technical articles for fun knows, Galois counter mode is a mode of operation for symmetric key cryptography, block ciphers, widely adopted for its performance. Those that know the ins and outs of these algorithms, and I'm not one of them, notice that this particular one could be improved by using vector instructions. Starting with JDK 18, when Vector API was in its third incubator, we did precisely that. Use the Vector API in the security libraries that computes AES JCM. In case you're wondering if it's okay to rely on a preview or incubator API, it is okay only if you are committed to updating your code with any change to the preview in later versions. And we are, so it's all good. RISC-V. This is an open source RISC instruction set architecture. It is supported by many languages, many toolchains, and RISC-V hardware is becoming more common. Moving the port of RISC-V to the OpenJDK mainline does not imply that any vendor will provide RISC-V ports as part of the Java offering. You will see in later slides, when I show you what operating systems and architecture Oracle will provide JDK 19 for, that we do not plan to have RISC-V offerings yet. What this JEP means, though, is that whenever a vendor decides to support RISC-V, it will be easier, and more importantly, that this architecture will be taken into account when designing and implementing new features. The last two JEPs in our list, are the first previews that arrive into the JDK from Project Loom. For those that haven't seen any of the Project Loom presentations, Project Loom aims to revamp the Java concurrency model so that it can meet the needs of today's high-scale server applications. Why did we need Loom? Even from the first release of Java, the platform has allowed for written concurrent code using a very straightforward model. Java threads, when first introduced, allow for a platform-independent way to write concurrent code. Without Java, developers who wanted to have different tasks running on different threads often had to deal with platform-specific code. Java provided a nice layer of abstraction that let developers use Java threads, which would then magically be converted to operating system threads for each of the supported operating systems. There is a lot of great things about these threads. They offer a natural programming model with readable sequential code using control flow operators that users understand, loops, conditionals, exceptions. Users get great debugging and serviceability and readable stack traces. And threads are a natural unit of scheduling for the OS. Project Loom aims to retain all of those advantages. The problem is that the implementation of threads by the OS is too heavyweight. It takes too long to start a thread. But worse, the number of threads that the OS can support at any time is limited by limits the number of concurrent transactions that a server can handle. Now, if you're using threads to service operations that spend a relatively large amount of time waiting for resources, for example, if you have a server handling requests that come through a network, the limit in the number of threads can severely limit your application to well below the capacity of the hardware or the network. And so, threads become a severe constraining factor on server throughput. One option to deal with this limit is to turn into the reactive frameworks. By not representing concurrent operations directly as thread, we can scale well beyond the limits posed by the thread per request model, but at a very huge cost. It is much more complicated and it's harder to write, it's harder to read, and it's much harder to debug or profile, because the platform in all of its layers and all of its tools is built around threads. Reactive may be the best that people can do with the current JVM, but Loom's goal is to do better, which we can do by making threads lighter and more scalable, letting people keep using their simpler models and toolings that they have been using for years, but gaining a lot of performance. From a user perspective, Loom has almost no new APIs. The main new runtime construct is virtual threads, which shares today's threads APIs and semantics. But they're implemented differently from existing platform threads. Rather than being tied to an OS thread and carrying around a big contiguous stack, virtual threads store their stack in the heap in the form of delimited continuations. A virtual thread has a couple of 100 bytes of metadata, starts up much faster than a platform thread, and uses only as much stack space as is actually needed for the active stack frames. As a result, we can create many more virtual threads than we can platform threads. When a virtual thread has work to do, the JVM assigns it to an OS carrier thread until it reaches a point where it would normally wait for some resource. The JVM will then move that virtual thread out of the carrier thread and place instead some other virtual thread that is ready to get work done. When the resource that the thread was working for respawns, the thread can be allocated to some other carrier operating sister thread. It could be the same carrier thread or a different one, it really doesn't matter. The whole scheduling of the virtual threads to carrier OS threads is handled by the JVM. As a developer, I don't need to worry about it. I can write code like I did before and let the JVM figure out when to have one of the virtual threads running, when to pause it, and when and how to bring it back to more work. Because they're real Java threads and not some other abstraction, existing code and tools that use the Threads API just works when running on virtual threads. They work with thread local, they give you the same stack traces and thread dumps, and they work with the same debugger and profiling tools. This graph shows Jetty configured with 200 and 800 threads using a task which has a 100 millisecond IO-bound service latency. As little laws would predict, we see in the darker blue line that the server handles the load fine until we push the requests per second above about 10 times the number of threads, at which point latency becomes terrible, since the arrival rate exceeds the service rate and requests start queuing up in socket layer, and then eventually they start being rejected. But at that point where the server becomes overloaded, we still have plenty of CPU headroom. On the lighter blue line, we can see that we can postpone the time when requests start to get rejected by letting the JVM create more platform threads. But if we continue simply adding platform threads, which requires so much memory, even if they're not using it, we would run out of memory long before we could approach the point where the CPU is being properly utilized. The green line is the graph that shows the same workload running with Loom and using virtual threads per HTTP request. Now we can continue to scale until we reach full CPU utilization. The graph doesn't show that point because we had a hard time generating enough load. If you had workloads that are already using all the CPU, then Loom wouldn't make that much of a difference. But in most cases, when you use threads, the bottleneck is the number of OS threads, that is currently capped by memory. In those cases, Loom can remove that bottleneck and let you scale the number of threads until you are limited by the number of cores. As part of the work to test Loom, a small group of people from the Helidon team, and by small I mean one person full-time and one person part-time, worked to create a prototype replacement for Netty, which they called Warp. Netty is used to create high-performance protocol servers and clients. To allow for optimal resource utilization, Netty doesn't use the simple paradigm of one Java thread per request, but instead it has its own set of APIs to allow multiple requests to time-share the same OS threads. Netty is a mature product, actively maintained since 2004, so it has about 18 years worth of hard work and optimizations. Using Loom and dumb synchronous code, some tuning, the Helidon team was able to get similar or better performance to Netty in just 6 weeks. And, perhaps more importantly, the code for Warp is much easier to read, maintain, and debug. We get a nice quote here from Thomas Longer from Project Helidon, how they never encountered some of the problems that they had expected to run into. A great deal of the work of Loom had nothing to do with stack swapping magic, but in clearing roadblocks in the JDK to make it all work smoothly. This meant finding all the places in the JDK where blocking might happen and replace it with logic that, if running on virtual threads, would instead pause the virtual thread and free up the carrier thread. Much of this was undertaken in separate JEPs, where individual JDK components were re-implemented and they were put into JDK 13, 15, and 18. This had the extra benefit of not only making these mechanisms Loom ready, but it cleared up a bunch of technical debt on some old code. In the end, Loom made almost no significant changes to the JDK APIs, except for the new structured concurrency API. Instead, it provides better implementation of existing and familiar abstractions. We've been working on Project Loom since late 2017. We had a prototype of the core feature, then called Fibers, now called Virtual Threads, in the first 18 months. But as usual, most of the work of getting to a production quality release was not in the core feature itself, but in the things adjacent to it. It took several iterations to get the performance where we wanted, and much of the work was rewriting the implementation of Java's old I/O subsystems to eliminate blocking and getting the debugging experience just right. Some of these improvements have shipped already as part of separate JEPs. JEP 425 introduces virtual threads as a preview features to the platform. For most developers, switching to virtual threads will simply require switching from platform threads to virtual threads. But there are two scenarios in which virtual threads cannot be unmounted during blocking operations because it's pinned to the carrier. One, when it executes code inside a synchronized block or method, and two, when it executes a native method or a foreign function. The Java team has taken care of updating most of the code that did this within the libraries. In some cases, however, your own code might still have some of these issues. The new APIs give you the right tools to update your code so that it can play nicely with virtual threads, but you still need to find out the right places to update. To help you with this, a JDK Fly Recorder event is emitted now when a thread blocks while pinned. The system property JDK trace pin threads triggers a stack trace when a thread blocks while pinned. Running with dash djdk.trace pin threads equals full prints a complete stack when a thread blocks while pinned, with the native frames and frames holding monitors highlighted. Running with dash djdk.trace pin threads equals short limits the output to just the problematic frames. JDK 19 also delivers APIs for structured concurrency. It is a relatively new idea in its current form, but it wasn't ours. The Loom team found it in a blog post that it's of the rare kind that makes them go, obviously this is how things should work. The principle is simple. When sequential code splits into concurrent flows, they must join back in the same code unit. But the implications are profound. Just as structured programming codified best practices into the language for sequential code, structured concurrency does the same for concurrent code. Many of the most complicated parts of Brian Gett's book, such as those on shutdown and cancellation, just go away. Structured concurrency codifies these best practices of propagating failure and cancellation into the API so that they cannot be done incorrectly, as well as expresses their relationship in a way that the runtime can understand and recreate the structure in the structured thread dump. Because it follows a discipline of waiting for child tasks, some of the most error-prone aspects, such as cancellation and shutdown, are made dramatically simpler. And this brings us to the end of the JEPs in JDK 19. Let's view some of the other details of the release. Where can you get it? You can download JDK 19 from the Java site in Oracle's website, where you will find links to the current updates for 17, 11, and 8, as well as JDK 19. You can also download these releases under the no-fee terms and conditions using curl or wget. The URLs for those releases can be constructed by specifying the version, operating system, architecture, and packaging format. We have two different sets of URLs. One has latest in the path and will get you the current version, whatever it happens to be at the time when you request it. The file name on the current version is just the feature number rather than the full version. So for example, you can ask for JDK 17 instead of having to say 1704. The archive URLs have archive in the name and have the full version. For all of the URLs, you can get a checksum by adding a .SHA-256 to the download URL. As you would expect, JDK 19 supports the same operating systems as previous JDK versions, but we also add some of the newer updates like Oracle Linux 9 and macOS 13. For Linux and macOS, we support x64 and ARM64. And as usual, the best place to learn more about any of these features is openjdk.org, where you will find the complete list of all of the JEPs, and it also includes most of the text from which I got the information for this session. I hope you found this information useful. I invite you to download and use JDK 19. If you do try out any of the preview features or incubators, we would really appreciate you letting us know how it goes. Each JEP has a link to the correct email alias for where to submit your feedback. Thank you.